Well, welcome everybody. Thank you so much for joining us for the first Ingenii meetup. We're really excited to do this ever since we launched our community. Um, we wanted to give you guys a little snapshot of the people that have, are participating today. We are all the way in the U.S. as well as all the way on the other side of the world. Some people in India, Bangladesh. So good morning to those of you in the U.S. and I hope you've had a great day, and good evening to those of you a little bit farther east. Hopefully you can see this map. But as we continue to grow, we'll continue to fill in some of these countries and have more and more people from around the world. So we're really excited about that. And we're really excited that you're all able to join us. Hopefully you guys can hear me. I know one of the members just let me know they can't hear. As long as the majority can hear, I think we're good to go. Great. So aside from being all over the world, they have a vast amount of interest across quantum computing and quantum generally. We're really proud to have brought in so many different and diverse studies across the industry. For us here at Ingenii, we're focused primarily right now on QML and the applications in healthcare, things like drug discovery, medical imaging, and but we do see the massive impact of what quantum can do, and that's why we want to continue to draw upon the community and give everyone in the world a place to grow together and learn from each other. So you can see here, this is just a couple of the topics that a lot of the participants today entered in kind of our form. So you can see that there's a ton of diversity. And that will just continue to grow as our community grows and we continue to share things with each other. So I'll just say, in case you're wondering who's this talking head, I'm Annie Ratner. I'm the behind the scenes on the Ingenii Discord. So if you've got my notifications, this is me. I apologize if I'm bothering you in the weird hours of the night.
Face to the name.
Yeah. But if you have any suggestions ever about the community or feedback, you can always hit me up. I go by Annie in the Discord. I also am the Ingenii account, so feel free to reach out anytime. But with that, I just want to say welcome. Thank you guys for being here. This is really exciting, and I'm going to pass it off to Christine.
Hi, everyone. So I'm the CEO and co-founder of Ingenii. As most of you know, we're on a mission to accelerate the adoption of quantum computing within life and environmental sciences. And I think for the most part with this group, I don't have to tell this group how paradigm shifting quantum technology is. It's really changing the way that we design drugs. It's changing the way that we're modeling our natural systems, the way that we're thinking about our diagnostics, and there's so many other vast applications. And that's why we're really excited to bring, the community together, because it's not just a small team. We really view this as trying to pull together all of these, innovative minds and expertise to solve some of the world's most pressing problems, right? That's really, at the end of the day, really what we're pushing towards. So don't be shy, share your ideas, share your questions, share your thoughts. We want to hear from you. We want to see you presenting your research. We want to kind of be able to build with all of you. So please, engage with us and find ways that you can kind of interact. At Ingenii, we are a small team of 4, but we are augmented by our academic research program, which is basically PhD and postdocs who come and work on different various projects with us. We also have our strategic academic partnerships with Purdue University and University of Chicago. So we're doing a lot of really interesting work there. And then we've got our community, which is you guys, right? And this is at the core of everything we're building. So as far as our core team of leadership, we've got myself and my co-founder, Marco, who he oversees the technical and product side of the business. We've got Greg, who oversees our data engineering. We have Annie, who oversees all of our marketing and community strategy. And then last but not least, we also have Laia, who's our chief science officer and has been spearheading all of our quantum development and research so far. So with that, I'll actually go ahead and Laia, I'll hand it over to you.
Thank you, Christine. Thank you for this nice introduction. Okay, guys, so today I wanted to talk a bit about quantum machine learning, which is our primary focus currently at Ingenii. So I'd like to start by, briefly introducing the concept of quantum computing so that we're all on the same page. And then I want to talk a bit about quantum machine learning and in particular quantum neural networks. And we'll discuss some of the applications that we're developing here at Ingenii. And just feel free to interrupt me, ask questions. I would be very happy to do like an interactive session with you guys. So let's get started. So let's talk about quantum computing. So quantum computing works in a fundamentally different way as classical computing. So in classical computers, the basic units of information are called bits, and you can think of them as a switch. They can either be 0 or 1s. However, in quantum computers, this works differently. The basic units of information are called qubits, and you can think of them as an arrow pointing in some direction in space. So okay, so someone is saying that we cannot interrupt. Okay, just write the questions in the chat, and Annie can ask me the questions.
Yeah, I'll make sure that we can get your question answered if you just drop it in the chat or raise your hand.
Yeah, great. Okay, so we're talking about qubits. So qubits, you can think of them as an arrow pointing in some direction in space. So if it's pointing up, it represents a 0 state. If it's pointing down, it represents a 1 state. But the fun thing about qubits is that they can also be pointing in any other direction in space. And this property is called superposition of quantum states. And it's nothing more than a probabilistic mixture of the basis states 0 and 1. And this means that if you measure these qubits in the 0 1 1 basis, if you have, for example, this qubit here that's pointing in a certain direction in space, when you measure this qubit, you would get 80% of the times the value 0 and 20% of the times the value 1. And this superposition is one of the key properties that allows to design these very powerful quantum algorithms. And there's another property which is even more interesting, which is called entanglement. And entanglement refers to the fact that qubits, you cannot think of qubits independently. In classical bits are independent from each other. So if one bit has the state 0, it doesn't give you any other information about the state of another bit. However, with qubits, this is different. You have to think about qubits as being part of a larger quantum system. And this means that if you change the state of one of the qubits, you're changing the whole state of the system. And this can in turn influence the state of some other qubit. And this happens no matter how far apart these qubits are. And this is why Einstein referred to this weird property as spooky action at distance. So these are the two properties that make quantum computing so special. But that being said, quantum computing is not the next iteration of supercomputing that would accelerate any kind of computation, but rather it's a different way of designing algorithms that allow us to design these algorithms that can speed up certain computational tasks. So it might be very useful for certain problems, but it doesn't mean that we're going to replace our laptops at home by quantum computers, at least not in the short term. Okay, so this is a brief overview of what quantum computing is, and there's a lot of progress both in hardware and also in developing error correcting and error mitigation strategies to try to overcome the problem of noise in current quantum devices. So among all of the algorithms that you could define, I wanted to talk today about quantum neural networks. So quantum neural networks are machine learning models that combine the concepts of quantum computing and also artificial neural networks. So let's start talking about classical neural networks. You can see here on the left the architecture of a standard classical neural network. And you can see that it consists of 3 layers. The first layer is the input layer, which maps the data of your problem into this network of interconnected neurons, this classical neural network. Then we have our hidden layers, and the hidden layers are designed to unravel the hidden patterns of data to find these useful features that are going to allow us to predict the output. And finally, we have our output layer that gathers all this information and predicts the final output. So all these neurons that you see here have hidden weights and biases that need to be learned. So during the training phase, you would basically give some examples to this classical neural network and then fine tune these hidden weights so that it learns to produce a certain task. So this is the typical structure of a classical neural network. What about quantum neural networks? Well, quantum neural networks are similar to classical neural networks in terms of the types of layers that they have. So you would start with also a data encoding layer that would map the classical information, the data of your problem, into a quantum computing system, which in this case could be a quantum circuit. Then you would have the variational model, which consists of quantum gates that perform operations of on qubits and change their state. And this variational model has some training parameters that can be fine-tuned. And then you would have the measurements that would recover the classical information back and would output the predictions of your model. So training this neural network can be done in a very similar way as in classical neural networks. So you would calculate a loss function and then perform classical optimization, changing the parameters of the variational model to fine-tune these parameters and find the best ones for a specific task. So this is a quantum neural network. And now you might be wondering, what is it different about quantum and classical neural networks? Why should we use quantum neural networks instead of classical neural networks? Well, there are different advantages of quantum neural networks. The first one is the high dimensionality of the Hilbert space, so the space where the qubits live. And this means that quantum neural networks can encode exponentially more data than classical neural networks. And this is because the space where qubits live scales exponentially with the number of qubits. So if you have n qubits, you could encode at most 2 to the power of n data samples. Well, not data samples, but numbers, like real numbers. So this allows working with higher dimensional data. And related to this is the lower complexity of these models. And this is because since these models have, well, they scale better with the number of qubits, they usually have fewer training parameters than classical neural networks. And the problem with classical neural networks is that if you want to define a very powerful classical neural network model, you're going to need vast data sets, long training times, and computationally expensive resources like GPUs, for example. So with quantum neural networks, since you're using fewer qubits, you're probably also going to need fewer training parameters, and this requires, in turn, shorter training times and smaller data sets and less computational resources in this sense. So this is the second advantage. And finally, quantum neural networks can also be useful for specific tasks. And these tasks are the ones that contain quantum data. And by quantum data, I mean any data that represents a quantum mechanical phenomenon. For example, molecular simulation. Usually, since quantum neural networks use quantum operations instead of classical operations, you can find better embeddings of data and better operations to do in data to uncover the hidden information from it. So using these kind of embeddings might be better than using classical neural networks in some applications. So this is all about quantum neural networks. Now I wanted to present 2 examples that we developed at Ingenii using this technology. And the first one consists of using hybrid quantum classical neural networks for drug discovery. So let me give you a bit of context. The goal here is to cut expenses and duration of the early stages of drug discovery. So once a new biomolecule has been proposed to be a potential drug, before going to clinical trials, it has to undergo a very throughout computational study. And this is because you want to make sure that this drug has the correct properties before actually testing it with patients. And this study it's very expensive and it actually takes quite a lot of time to do. So if we can accelerate these early stages of drug discovery, at the end of the day, the patients can have their treatments faster. So this is the overall goal. And there are many ways that we could tackle this problem, many ways that we could try to improve this process. And in this example that I'm showing here, we are going to predict the interaction between a new molecule that has been proposed as a drug and the target proteins in our bodies. And this is called predicting the binding affinity. And it's important because once you design a new drug, you want this drug to target selectively certain proteins so that it performs its function correctly. And this is a very complex task because there are many, many factors that influence the binding affinity of a drug and a protein. So to tackle this problem, we designed hybrid neural networks to try to both reduce the computational time and cost derived from using GPUs, and also to improve the performance of the state-of-the-art models. So the current state-of-the-art models are neural networks, which have lots of training parameters that are very complex neural networks. And one of the state-of-the-art models is a three-dimensional convolutional neural network. So the first project that we developed consisted on replacing some of the heavy layers of this convolutional neural network by quantum circuits, by quantum layers. And in this way, what we achieved is we reduced significantly the number of training parameters because these quantum layers had much fewer training parameters than the classical version. So we obtained like a 20% savings in training parameters, and this in turn meant savings in training times and costs derived from GPUs. So we obtained 20 to 40% savings in these training times. So just by combining classical and quantum, we could really simplify this model and allow to train these models much faster, so that we can explore more these kind of neural networks. So this was the first part, and then the second part, we combined two existing classical machine learning models that look at the data in different ways. One was a convolutional neural network, and the other one was a graph neural network. And since these models looked at the data in different ways, we could extract the features from these two models and then combine them using a quantum neural network. And by doing that, we compared the performance of this model to the one we would obtain replacing this quantum neural network by a classical neural network. And we saw that the quantum neural network provided better performance. It wasn't like super significant, but it still was a very challenging advantage. Like, it's not easy to improve this kind of performances. And also we saw better conversions of the loss function. Yeah, Annie.
Yeah, it looks like you have a question in the chat.
Ooh, I do.
Yeah, you have a couple.
Oh, what was the dimension of the data? So the dimension of the data, we were using 3D boxes. Like the input data was the position of the atoms in space in a 3D domain, and therefore and we had a size of 48 in each dimension, so it was 48 times 48 times 48. And we had different features. I think we had 19 features, giving information about the properties of the molecule, like the types of atoms. Like, we had like a one-hot encoding of each atom, and then chemical properties of this data. So we had like 48 times 48 times 48 times 19, and I think this is a very large number. I think it's in the order of millions. So that was the input of the data. Then how many qubits? That depends. Here we didn't try to encode the whole image into a quantum circuit yet. We were trying to look at local patterns in data. So we were using 8 qubits to encode 8 times 8 times 8. But you could encode the whole data with, I think, like 30 qubits, or around that number. But for now, with the current stage of quantum computing, we decided to take like fewer qubits. But even with that, we could find a significant advantage. This was one question, so please let me know if if I answer correctly. And then the second question, I think it's the same thing, basically. What was your data size? Yeah, same thing. And what encoding method? So we use a flexible representation of images, of quantum images, because, well, it was very suitable for the type of image. So even though our data wasn't an actual image, it was an encoding that scaled logarithmically with the size of the data. So with the number of real numbers encoding the classical data. So that was very suitable for this problem. And it's a method that's specifically designed for images. And we had a 3D block, which was like similar enough to a 3D image, if that makes sense, like a video or something. So basically, we use like one qubit to encode like the position of the element of the matrix, so like the position of the pixel, if you want to think in image terms, and then another qubit for the actual value of this pixel, which is like the value of the data sample that we had. So, okay, I'm going to continue, and if you have more questions about this, just write it on the chat. So I was saying basically that, well, we developed this first method to reduce the dimensionality, the complexity of this classical neural network, and then we use this quantum fusion model to combine two different state-of-the-art methods and make a better performance out of those ones. And for that, we use the quantum neural network. So basically, the key idea here is that we use these methods, we achieve better results, and these are not particular to drug discovery. These are really just particular to neural networks. So if we had a different problem which also used these kind of neural networks, we could also try to accelerate the training and improve the accuracy using these strategies. Okay, so this is one of the applications that we did, and then we're currently developing another project in medical imaging.
It looks like you have one more question.
Thank you. Did you experience variant plateau phenomena while training the quantum neural network? I think this is a huge problem. Yes, actually our training was very smooth. Like, it was even surprising that the convergence of the loss function didn't really get stuck in any local minimum. But it's true that this is actually I really like a really complicated problem, and to solve that you could try, well, you could change the architecture of your quantum neural network, but you can also try to freeze some layers and train some of the layers like separately, so that the network is not that deep, like the circuit is not that deep, because you're like fixing one of the training parameters. So this is one of the things that you could do, but it's true that in this case in particular, we saw a very smooth training of the neural network, so we did not have this problem. Then we have another question. No, we use one-hot encoding for the atoms. So sorry, that might have been misleading. So our input data was a matrix, a 3D matrix, which had size 48 times 48 times 48 times 19, and these 19 were 19 features that we extracted. So, for example, we extracted the one-hot encoding of the atoms in the image. This means that one of the features was a hydrogen atom, for example. Well, actually, not hydrogen, but oxygen atom, for example. And then you would have the one-hot encoding of the positions of these oxygen throughout the 3D space. This was a one-hot encoding, but I don't mean that then we did one-hot encoding, like we didn't do basis embedding, if that's what you mean. We didn't use like we use this flexible representation of quantum images, which has a logarithmic, uses logarithmically number of qubits. So the other question, when you say you had a huge advantage, the huge advantage, well, I'm not sure if I could use the word huge, but in the second problem, when we were trying to improve the performance, it was a regression problem. So we were trying to predict a number, which was this binding affinity, which quantifies the interaction of the protein and the biomolecule, and we had like between 5 and 10% of improvement, which is not, I wouldn't say that it's huge, there's way to go, but we were really, like, these are really state-of-the-art methods, so it's really hard to outperform this kind of model. So that's why I think it's a win to use quantum neural networks. But it's true that probably even just changing the feature extraction or some part of the data, we could do better. But I think it was even impressive that we could see some kind of advantage. So okay, I was talking about medical imaging. Okay, so yeah, we're developing another project using quantum machine learning for medical imaging, and this is an ongoing project, so we still have a lot to learn. But basically, the problem here is that there are a lot of misdiagnoses in the U.S. Actually, like 12 million people get misdiagnoses every year. So really, automatizing this process and improving the diagnostic accuracy is really important for many different diseases. So, and there are again a lot of things that we can think about. but here we're focusing on medical imaging, and in particular, we're working with breast cancer. And I wanted to show you our approach. I know that here you can see a brain and not a breast. I know, but I thought it was like more visually useful like this. And the method that we're developing is really should be useful for many problems. So let me finish this, and then I'll look at the questions again. But basically, solving medical imaging diagnosis, it's very hard. There are a lot of things that you could do in this space. So really what we're thinking about is, instead of just like replacing one machine learning method by a quantum machine learning method or by another quantum algorithm, what we're thinking about is designing a whole pipeline that can help improve the diagnostic in general. So basically, there are many problems when trying to generate AI models to automatize diagnostics. So the first one is the lack of data. So when you want to train a complex machine learning model, you're going to have to need a lot of labeled data samples, and this is hard because this requires that the doctors have to actually label those data and validate them and so on. So usually the data sets that are available are not that big, and this is why one of the things that we could do with quantum is maybe do some data augmentation. So using quantum generative models, we can try to generate artificial samples that still make sense and can be used later for training. Then also the image quality. Sometimes there's low contrast, or there's a lot of noise, or maybe we just want to find a good representation of these images for the AI model. And here we can also try to use quantum filters or any quantum preprocessing method to try to prepare a better image for the neural network. And then we have the neural network itself. And we saw that we could accelerate the training of classical neural networks using hybrid models. We could try to do the same thing. And here the models are more segmentation rather than regression, because you want to identify the region where the tumor is located. So we could try to do some reduction of the training parameters using quantum methods, and also try to improve the accuracy by combining these hybrid and quantum and classical machine learning models. So really there's a lot to do, and I would be really happy to hear your ideas, what you think about this. But we are developing some parts of this pipeline right now. But there's a lot that can be done in this space, I think. So there's a lot that we can do to improve diagnostics. And this is our current state. So let me go back to the questions. I don't know where I was. So in the hybrid QNN, can you put the QNN layer between the neural networks layered compared to the convolutional at the end? Yes, you can put quantum convolutional layers. In our case, it was like at the beginning, but you could have a classical layer and then a quantum layer. I don't think that should be much of a problem. We use it at the beginning because at the beginning it's the one that has like larger size. Then you do the pooling of the classical neural network, so the size is reduced. But in theory, yeah, you could combine them however you want. It's true that we would have to think what makes more sense. Why would you want to have some classical and then some quantum and not quantum classical, or well, any architecture that you choose? But yeah, in this sense, neural networks are in general very flexible. So I believe hybrid QNN means that you're using parameterized quantum gates to learn weights and use yes, agreed. And yes, you're using a classical neural network and a quantum neural network, and you optimize both with classical optimization. So yes. And then you say that you're confusing hybrid algorithms like BQE. Well, it's still a hybrid algorithm. The thing is that you have classical layers and quantum layers, but we optimize both classically. But yes, which we use backpropagation here. Yes. Yep. Okay, so I think that's the end of my presentation. I know it's been a bit like interactive, going on and off, but I think it's been fun. So yes, this
Well, I
is,
have one more point, if you wouldn't mind touching on
yeah.
it, that I think the group might find interesting. I know we don't have slides for it and it's very, very high level, but would you mind talking about the CQE hackathon? Because that was also an application of neural networks bridging between diagnostics and drug discovery a little bit with the clinical trials. And I know there's a lot of work to be done there, but would you mind just talking about that project and, just some of the findings that we got out of that, weekend?
Yes, that was a very exciting hackathon. So basically, the problem was to improve diagnostics for mental health disorders. And the idea is that, once what you think that you have a mental health disorder, you would probably go to a physician, and then you would like answer some questions, and then you would get diagnosed, and then you would send to the appropriate treatment. But many people don't actually go to the physician, maybe because I don't know why. Maybe because it's far away, maybe because they're not used to this kind of health treatments. So the challenge that was given to us was um, to build an explicable rule-based machine learning model, quantum machine learning model, to automate all this process of diagnostics in mental health. So that is that once a patient has answered a certain questions regarding a mental disorder, we would pass that through a machine learning model, a quantum machine learning model, to predict the probability of having a certain mental disorder or having multiple mental disorders. And the key idea here is that they wanted a model that was explicable, so that the doctors could identify the questions that were more relevant to make that diagnostic. So the approach that we developed, we only had 1 day and a half, so I'm sure we can improve that. But the approach that we did was to train a quantum neural network to predict the probability of having a certain mental disorder or condition or whatever. In this case, we were working with autistic disorder syndrome, but we could work with any other any other problem. So basically, we developed this quantum machine learning model, and then we trained a quantum neural network that would learn to predict these probabilities for depending on the questions that you answer. But then we went one step further to make this model more like explicable, interpretable for doctors. And then we use a trained model to sample marginal probability distribution. So what is the probability of having this mental disorder given that you answer these two questions in this way? And what we could do is we could identify the pairs of questions that gave a larger probability of being diagnosed with this mental disorder. And the key idea here is that by using quantum computers, we could sample these probabilities directly. We wouldn't have to aggregate all these probabilities as we would do classically. So this was much faster to identify the smaller set of questions that lead with high probability to a certain diagnostic. So this is what we did, and I think we could combine this with many other things. I think we could expand the data to take into account other information from patients, and I think we can definitely improve the hybrid approach that we have right now. And we could look, instead of just pairs of questions, we could look at triplets or different combinations. So that's very interesting, and I think it could have like a very large impact on the area.
And then the overlap in the drug discovery side, right? Once we optimize the diagnostics and we know that we're really nailing down, the diagnosis, we can really optimize the clinical trials. And that's actually one of the biggest failures within the clinical trial process, is not having the right patients in the clinical trials. So the more we can get really efficient with the selection, it really overlaps into huge amounts of savings and optimization, as they go further down the pipeline. So I thought it was so interesting that it touched kind of both sides of what we're looking at. So thanks for digging deeper in that.
Yeah, and that's why you did the business part and I did the technical part.
And I think we had one more question, or two. I guess the other one was a comment, but
yeah, it's super exciting that someone's working on quantum image segmentation. I would really like to follow up with you. Yeah, I think that's super exciting, because we're also building something in this space, and I would really like to know what you're building. So Yeah. And quantum image encoding is flexible representation of quantum images. Yeah, I think it's a bit hard not to draw it, but you can Google it. But basically, it uses. So imagine that you have like a 2D image that would make it. Hey, thank you. That will make it easier if you have this 2D image, and then the computational basis of if you have like a 4-pixel image, the computational basis of 2 qubits would give you the position of the pixel. So you would have 0, 0 for the top left, 0, 1 for the top right, and so on, and 1, 0, 1, and 1, 1. So these would encode the position of the image, and then you would add an extra qubit to encode the value of the pixel, so the value of the image. If it's black and white, for example, so a value between 0 and 1, you could codify it as an angle, and then, well, just like apply like angle embedding to that extra qubit. So since the dimension of the image is what scales, basically, the value doesn't scale, it's just a number. This embedding, this encoding scheme scales logarithmically with the number of qubits. So it's basically the logarithm of the number of, sorry, not the number of qubits, the number of like matrix elements that you have, pixels. So it's basically the logarithm of that plus 1 because you have an extra qubit. But yeah, I think it's better if you just like look at it. It's better to understand.
Let's try to answer these 2 questions and then move on so we can give Abu some time. We have our community presentation today.
Yeah, that's a very good question. We did not train this in quantum hardware yet. Yes, and it's true because the back propagation cannot be applied there. We adapted the algorithm so that it could be trained on GPUs, and that's why we didn't encode the whole image in the quantum circuit. But I think it could still be done in quantum hardware, and of course we would have to change the optimizer. But we're now partnering with AWS Bracket, and they have some quantum computers available, and we're going to test some of the of training of these algorithms and see how it works. We did try some noise models and see how that affected the performance. And how much a training time took in the I think that the relevant one, which is the hybrid 3D CNN, it took like 20 to 40% less time, and the hybrid one than the classical one. In the other one, I don't have the specific numbers. It's true that the quantum neural network took longer in this case than the classical one, because the classical one was like a very simple, well, simple enough machine learning model. But here the importance was the performance. And we trained this on CPU as well. Like if we had trained this on GPUs, it would probably have been faster. But I think that's it, guys. Yeah, so I think we can go to our presenter.
Yeah, and if anyone ever has any more questions for Laya about anything we discussed today, or even outside of that, the Discord is a really great place to do that. Just you can send her a direct message. We'd love to see it for the group, because I'm sure if you've got a question, someone else has it too. So yeah, feel free to use the Discord, and as always, provide some feedback if you have any suggestions. For the presentations today, unfortunately, our first presenter is not under the weather, so he's not going to be able to make it, Mohammed. But we will be sharing some of his content on quantum safe cryptography that he was able to send through on the Discord. So if you came and you're really interested in that, just wait to see it on Discord later today. But we do have Abu here, and we will pass it off to him to discuss quantum classical hybrid sentiment analysis.
Today I'm going to present the quantum classical hybrid sentiment analysis. So before talking, I just want to ensure that right now fully quantum based or quantum machine learning system is not available. So we need to rely on the classical system. So actually recently we are doing a research on the hybrid classical quantum sentiment analysis on the 2 different data sets. So here I'm presenting in details. So why actually sentiment analysis is important? Actually, sentiments contain the opinion of human in rely on some specific topic like customer feedback, brand promotions, product development, financial service, healthcare. Like if we want to the patient review, then we need to rely on their satisfaction level. So also medical and entertainment purpose, like if we calculate or if we want to measure the any movie review from their rating, so we need to depend on the reviewer comment. So detecting online abuse or cyberbullying is important for a sentiment analysis. That's why we are thinking to make a hybrid model for detecting any sentiment analysis problem. So our initial research is we are trying to apply different qubits, um, rely on the features, because we know the NLP model have need to depend on the features. So there is some features dimension like in our research we are facing this problem to reduce the features, because when we throw a big data set of natural language processing or text, there is a huge number of dimension is present. Like in our two data set, one data set we have 2000 dimension, another data set we have almost 500 dimension. So how can we reduce this dimension to calculate in qubits, and how can we convert the data? So before that, our research is basically collaborating the classical system and the quantum system. So we are using dimension reduction technique and also data compression method to reducing the features and dimension for the quantum system. And we apply QSVM, that means quantum support vector machine. On also we use the variational circuit for the quantum part, and in classical part we are depend on the support vector machine, which is the SVM. And dimension reduction technique, we apply principal component analysis and data compression method. We are applied to wavelet transform for making the convenient to feed the classical data onto the quantum models. Actually, in the background, we studied that the right now current sentiment analysis or current text analysis problem in quantum actually all are rule based. They are fixing rules. There is no uh, automatically things are present in the current world. So we are utilizing that the quantum machine learning algorithm and the extracting the text and extracting the sentiment for the small amount of data. So our hybrid model is following automatic approach for both quantum and classical computing techniques, and we are we used to the performance. Actually, we are calculating the performance of quantum system, and if we compare the model performance with the machine learning classical machine learning algorithms. So here is our approach. We are using a previous dimension that we are using two data sets. Then we uh, classically we analyze the text. That means we pre-process the text, and we are applied word embedding technique for the extracting the dimension from the data. That means we at first we vectorize the text and calculating the dimension, and we reduce the dimension using PCA, principal component analysis, and also well, we need to compress the data set using wavelet transformation. After that, we send the features to the quantum feature map, which is a poly feature map, and we send to the classical system like a classical SVM, support vector machine classifier. After that, we are applied quantum classifier like BQC and quantum support vector machine. Then we can predict actually the sentiment is which class the sentiment is, like positive or negative classes. So basically, there is two distinct data set in our work, like English and Bengali, and there is our team members which are currently working with me, and our supervisor, Dr. Navid Mahmoud. He is also a PhD in quantum computing. So basically, the performance look like this. As we know that the already sentiment analysis is a established have a established result in classical system. So why we use the the quantum system, or why use the quantum method for calculating the sentiment? So there is reason is like we want to take the advantages of computational problem, like we want to increase the or reducing the training time, and also try to improve the accuracy. So in our initial research, there is some results, and we use three different qubits, 2, 4, 6, and we extract the features from principal component analysis. And sometimes the accuracy is better than the classical system, and sometimes the classical system is better. Even the good thing is like accuracy is always constant if we change the features, or if we change the the bit qubits, number of the qubits. And there is after the hard transformation, that means the data compression method level, we also calculate the training time for the each qubit, and we saw that the accuracy is still same, and it's put the consistency in test and train data sets. That's actually near to the classical accuracy. So in conclusion, I would like to say that what actually our plan, we try to integrate a model, and we try to build a model for the future quantum machine learning, which will actually for the natural language processing application, and also the quantum machine learning problem. So in near future, we try to the state of the art like BART model and all other. We also working to integrate BART model in using the quantum neural network. So it's actually also the hybrid approaches. So our existing methods are we are working on increasing the performance of algorithms. Right now, the current algorithms is similar with the classical or little bit less. Sometimes it works better for the classical. So we want to take the advantages for the quantum computational uh, accuracy. So in our classical methods, we exploring the error mitigation and noise reduction problem in future, and also we are trying to working on the GPU based system, and we try to replace the GPU to FPGA server. Our team is working on that. So actually FPGA is better for the quantum algorithms. So that's the my part. If you have any question, then you can ask me.
Thank you, Abu. It looks like you do have a question in the chat. I'm not sure if you're able to view it, but I can read it to you. What was the number of features that you used in the model after the reduction?
Yeah. We use to the principal component analysis. So most of the time we use 2 features, 3 features, 5 features, 6 features. This amount of features we use for the quantum data, because each feature contains each single number of qubits. So that's why we are using the classical PCA. Then classical PCA, we are using the data compression method using wavelet transformation. And after that, we just send to the data to the QSBM and variational circuit. So that's it.
So, any other questions?
I have a question. Abu, do you remember what kind of kernel of quantum kernel did you use?
A quantum kernel, we are using actually Qiskit, and actually I need to review the code again, so I forget the thing.
No, it's okay. No problem. I was just
Yeah.
curious.
Yeah, no problem.
And a question from the audience is that
Yeah.
whether you used angle encoding or what type of encoding you used.
Actually, we are using angle and amplitude encoding, both two.
Alrighty. Well, thank you so much for presenting. Oh, we got another one. We got more. Okay, how did you use,
Rolling in now.
they're rolling in. How did you use amplitude encoding?
How we use amplitude encoding? We use amplitude encoding like we make combination of Hadamard gate and RZ gate.
And did you use both the encoding strategies at the same time?
Same time, but it's actually sometimes amplitude encoding is better than the angle encoding. So we pick amplitude encoding when we are doing the experiment. So the problem is not regression; it's actually the classification problem.
Okay, and was it a regression problem that you solved?
Yeah. Can you just repeat the question again?
If it was a regression problem or classification, or what kind of problem?
It's I would say classification problem, not regression, because in sentiment we need to depend on the binary or multi-class. So like if the review is positive, it's negative, or it's any neutral. So it's basically classification problem.
And then we have another question. How did you encode numbers in the amplitudes?
How we actually we convert the data to the Hart transformation. We send the array to the array value to the amplitude parameter, amplitude encoding parameter. Then amplitude encoding parameter is predict the exponential value of poly feature mass. Actually, it's predict the state vector of from the poly feature mass.
And which qubit did you measure as the output?
In qubit, so we are fixing qubit like 2 qubits, 3 qubits, or 4 qubits. So it's actually basically depend on the qubits, which qubits actually the model is given. So it's depend on the value of vector value and the depend on the qubit. Like if we measure the 2 qubits, so we need to measure the parameter of 2 qubits or the state vector of the 2 qubit. If it's 4 qubits, then we need to measure the 4 qubits state vector.
Awesome. Well, thank you everyone for your questions. I know we're getting to time here. So if you want to reach out to Abu, he's got his email here on the screen. He's also in the Discord as well. And then as always, you can always reach out to me if you're having trouble finding someone or figuring out where to ask me questions. But yeah, I just wanted to say thank you guys all for participating today and coming to our very first meetup. We will definitely have more, and we wanted to just, yeah, thank you so much for being a part of this.
And if you want to present, let us know. If you have any interesting research and you want to kind of join and showcase that to the community, we're happy to have you.
Awesome. Thanks, Lorraine.
Yeah, thank you all.
All right. Bye.
Bye, guys.
Bye.